Yes, so looks like recording has started. Yes, so good morning and welcome to you once again in this class. So in the last class we have started our discussion on this power dissipation, right? Power dissipation in an CMOS inverter. We are focusing on this CMOS inverter. So the first one that we have discussed is the dynamic power dissipation. Dynamic power dissipation is when you are changing the output from 0 to 1 or from 1 to 0, but we have seen that the capacitor to charge this capacitor, like the power is only consumed, okay, from this VDD source, and to charge it means to change the output from 0 to 1, right? The required power, which is the dynamic power dissipation, is can be given by the CL VDD square into the frequency of this change in output node from 0 to 1, right? So from here we have also introduced one more thing, that with this term we have also multiplied another term, which is the probability factor, because we have discussed that probably not all the inverters which are present in a IC will be fed with the same clock, and if that is the case, right, if suppose for some clock, for some inverter, the input or change in output is not equal to the change, is not at the same rate as that of change in this input clock, in that case we have to introduce an probability factor, right? So so we have introduced that probability factor, and we have also termed that like this is can also be called as the switching activity. We have given a simple example. Say this is the clock continuously coming, but the output probably for some inverter is changing like this, okay, for some clock. And we can see here, out of these 8 clocks, so only we have a change from 0 to 1 only for 2 cases. So that way the transition probability or the switching activity is only 0.25 or 25%, right? So like that we can calculate. So here remember, this is the dynamic power dissipation, and this is the primary like type of power dissipation. Okay, this is the major source of power dissipation, and okay, in a modern IC, this is the major source of power dissipation. Okay, compared to the other other two types. And this only happens when it is changing. If this output is not changing, then there is no power dissipation, like when there is no dynamic power dissipation, right? Okay. Then if you see the next one, which we have already discussed in the last class, which is the due to the direct path, like power dissipation due to the direct path, because we have seen this from this characteristics or the voltage transfer characteristics of this inverter, which looks something like that in this region, where both the transistors are simultaneously on, and we have seen the current profile, right? Current profile means ID, like will also look like this. So basically during this region, VDD is shorted with the ground, right? There is a direct path, right? Shorted means basically direct path. Even it's not actually shorted, because it does has a resistance offered by this MOSFET as well as this MOSFET. But what I want to mean, there is a direct path between VDD and this ground. So if there is a direct path, then it will also cause some power dissipation. And you can also say from this from this understanding only, that this power dissipation is also sort of like when the transistors is operating only in this region. That means only when the input is changing, or in the other way the output is changing, right? When this input of this inverter is changing or the output of this inverter is changing, then only this phenomenon can arise. And from there you can also notice that we should also have some f term or the frequency term associated with this, right? Then we have also introduced we have also discussed like this part, like how you can estimate it, because ideal case we have seen that it is basically type of step input, like it is like changing the change in input and change in output type of simultaneous. But in practical case we know that it will not be the case. There will be an finite slope, and basically during this slope only both transistors will be on. And we have also know that during VTH region the transistor would be off, so transistor would be on only in this region. So depending on that, we have tried to did some simplification and try to find what would be the power dissipation in terms of this I peak, right? So so we have find the what is the energy consumed, and if you know the energy, then obviously it should not be much difficult to find the what is the power. So we have also find the power. So here from this and we have also seen the power dissipation is proportional to I peak, that is the peak current that is flowing okay, from this VDD. And in the later page we have discussed that this peak current depends on okay, this W by L ratio as well as on this input and output slope. That is very important. So input and output slope basically depends on what is the output load capacitance, right? So depending on the load capacitance, the output, the change in output or the rate of change in output will be determined, and depending on that you can also see what would be the I peak, right? Another important point is this W by L. So W by L is quite understood. If you have the wide, if you make the transistor wider, then I peak would be higher, and that way the power dissipation will also be higher, right? So the third thing which we are going to start today is the static power consumption. So what do you mean by static power consumption? Static power consumption is when the input as well as the outputs are fixed. Say if you have given 0 volt or VDD, fixed it. Okay, so if you fix it, then you know at least one of the means at least one of the for either for this VDD equal like V in equal to 0, one transistor would be off. For V in equal to VDD, another transistor would be off. So in that case, there is no direct path from VDD to ground. So that way we have earlier like commented on this fact, there should not ideally there should not be any static power dissipation. However, we'll see now that there will be some static power dissipation as well because of some non-idealities. So, okay, one of the issue I think that you will also appreciate that see, this is an NMOS, right? This is an PMOS, right? So let us consider this first PMOS. So for PMOS, this terminal, this body terminal, so far we have not discussed it because we have considered this body terminal is only we shorted with this source, right? So if you see the MOSFET configuration which is shown here, right? Gate, oxide, the source, this drain. So this source which is connected with VDD for PMOS, right? So this is PMOS, right? Is connected with this body, right? Okay, fine. And this is V out, right? This V out is here. This V out is another this connected with this P plus, right? So this N like this N substrate, right? This part N type is always connected with VDD, right? Now suppose if this V out is equal to 0, then you see this is an PN junction, and you have applied a higher potential with the N side compared to the P side. So that means you have reverse bias this. You have reverse bias this like a PN junction or drain to this substrate, right? So as a result, you know every reverse PN junction should have some leakage current. So it will also have some leakage current, right? So we can say then we can like represent this thing as like this is a P. So P, this is a diode, and this diode is connected with VDD, right? And you can see this diode would be in the reverse bias when this V out is lower than VDD. So that will also have some leakage current, right? Similarly, if you consider for this NMOS is also for NMOS also this body terminal is connected with connected with ground, right, to source. So it is a source. So it is N type and it is always grounded, and simultaneously P is shorted with this, so P is also grounded. So it is always a zero potential. Now think about some case where this drain terminal, which is basically N plus, is connected with some positive voltage, or this V out is some higher voltage than 0. Then that also makes this PN junction reverse bias. So we can also then illustrate this thing like this, right? No, probably I have to change the diode direction because here P is connected with the like ground, so it should be like this, right? So that way we can say like I know we can model this total phenomenon by introducing another diode here, right? The leakage current for this NMOS, right? Okay, so basically here this is the source of PN junction leakage current. Here this is the PN junction which is the source of leakage current, primary leak, right? But we also know from this that this leakage current for PN junction is quite small, like so typically leakage current is small. So let me write it. Typically leakage current in PN junction is small, right? That is true. But we also know this leakage current in a PN junction has a significant dependence on temperature, right? Because we know that every 10 degree centigrade rise in temperature, right, this leakage current becomes 2 times, right? For every 10 degree centigrade rise in temperature, this leakage current becomes 2 times. And you know, when you are operating a transistor, like there will be some power dissipation, and the power dissipation would would be like dissipated power would be radiated as heat, means that will rise the device temperature. So that way, all the junction temperature would not be at room temperature, but would be at higher temperature. So if it is say like more 60 degree, you know, temperature rises by 60 degree, then you can imagine how many times the you have to multiply to get the leakage current. So at elevated temperature, this leakage current would be an issue, right? So at room temperature, probably you can neglect the power dissipation, but at elevated temperature, you should consider the power dissipation because of this junction leakage, right? So leakage at elevated temperature, right? So that also gives you one idea that there is certain requirement while you are making some IC that you need to keep the temperature of the IC or control the temperature of the IC, right? So that's why you have seen, right, with different packages, right, of these ICs, like particularly for power devices, which the devices with handling higher power, you have definitely seen that it should also come up with some heat sink. So there is a big metal thing that has been connected, and right, so you have to do this, right? Otherwise the junction temperature inside this device will be so high that your power dissipation inside this will be dramatically increased. So to reduce that, and that will also damage the or deteriorate the performance of this device, because mobility is a strong function of temperature. So if the temperature is increasing, mobility will also degrade drastically, right? So you should have the proper heat dissipation technique. So one of the important technique is that just to use an heat sink. Like heat sink is one technique. Here you connect a big metal path compared to your IC. So basically you are increasing the area. So that will like dissipate the heat in a better way. Try to balance the temperature inside the device. In some cases, this only addition of this heat sink is only addition of the heat sink is not enough. You need to externally cool it. So maybe you have seen in some ICs they have given fan, right? External fan. So that is basically a cooling purpose. In some cases, probably they flow some liquid inside some microfluidic channel, okay, to cool down the total IC temperature. So there are different techniques by which you can reduce the IC temperature, because this temperature is another factor which also as a designer you should keep in your mind, because if the device temperature or the IC temperature is increasing, then the performance of the total circuit will deteriorate heavily, right? So this is another important thing. So this is from the point of view of PN junction leakage. Another leakage current which is important, and which is more important for this modern submicron CMOS technology, is the subthreshold leakage. So what do I mean by subthreshold? Subthreshold means basically below threshold, right? This subthreshold means below threshold. So if you see the ID versus VGS characteristics of any MOSFET, then it basically looks something like this, right? Below threshold, the current is almost zero from, so if you plot it in a linear scale, it will look something like this. This region current is pretty low or small, right, in this region, right? And that's why we have seen we have like in our like day to day calculation, we can estimate below threshold voltage the current is actually equal to zero, but it is actually not the case. If you plot it in a log scale, and you can see here, this is the threshold voltage. Below threshold voltage current is not actually equal to zero. Say this is an NMOS, okay, with threshold voltage positive. So this is also the same characteristics plotted in log scale here. Okay, so clearly you can see when you have applied VGS equal to 0, then what is happening? See, VGS equal to 0, you have finite amount of current, right? So think about it. You have kept here 0 volt, and you are you are assuming that there is no current which is flowing, okay, through this NMOS. That is not correct, right? Because of the subthreshold leakage, some current is still flowing through this, right? So this is the amount of leakage, right? Okay, now what is this maximum voltage that VGS you can go up to? That maximum voltage is VDD, right? VGS maximum voltage is VDD. That's the only permitted voltage. Like you cannot go beyond VDD, the supply voltage, right? Okay, now what will happen? You think about it from the scaling point of view. Suppose if earlier you are dealing with 180 nanometer technology, now we have reduced it 120 nanometer technology. Okay, then what will happen? Right, then you have to also reduce this VDD, right? Okay, so you have also reduced VDD, right? Let me, I think one of you have not noted. Yeah. So so say this VDD has reduced. Okay, fine. Then what would be the implication of that? This reduced VDD. When this VDD is reduced, right, to get an good overdrive, overdrive means VGS minus VTH. You should also reduce this VTH. So VTH also you have to reduce. Say the same curve you want to replicate, but you want to shift it towards in the more left side, right? Then probably you will get a characteristics which would probably look something like this, right? With a lower VDD. So when you are scaling the device, you have to scale this VDD. When you scale this VDD, you have to also scale the threshold voltage. But see what is happening to the leakage current. If you are not able to reduce this slope, that means this would be in parallel with that, then your leakage increases, right? Leakage increases. So that is the reason why for some, and this is called the subthreshold slope, and there is a limit till what like the theoretical limit is 60 millivolt per decade. You cannot reduce this subthreshold slope beyond that. So there is a limit, and you cannot make the slope type of wall of a like type of perpendicular like this. No, you cannot do that. So it has a finite slope, and if you consider the finite slope, you are replicating and you are scaling the device, then your leakage current is increasing. So as a result, the subthreshold leakage or the power dissipation due to subthreshold leakage is becoming more and more prominent in these subthreshold devices. Right. So there is a contradictory requirement, okay, from this point of view, scaling point of view. So you have to reduce VDD with scaling. Right. So as a result, when you reduce VDD, you have to also reduce threshold voltage, because if you do not reduce it, remember the current ID is proportional to VGS minus VTH square. Say we are considering for the long channel, but okay, but just to give you an idea. So current is proportional to VGS minus VTH. So what is VGS? VGS is VDD. Maximum current is VDD. Right, so let us write VDD minus VTH, that is square. So if you are reducing VDD, if you do not reduce this, then this current will also reduce. Right. So as a result, you have to reduce VTH. But when you reduce VTH, your subthreshold leakage current substantially increase, and your power dissipation will also increase dramatically. So, but from the point of view of power dissipation, you need to keep this threshold voltage bit towards in a higher side, right, to reduce the leakage. So you can see from this point, like you cannot reduce this VDD arbitrarily. There is some limit beyond which you cannot probably reduce it, because if you do further reduction, then this point, like due to subthreshold leakage, the power you will be dissipating, that will be enormous. Is this part clear to you? Okay, so huh.
Sir, so
Yes.
what should be the VDS for the subthreshold region?
Could you please repeat your question?
So what should be the VDS for this subthreshold region?
VTH for the subthreshold. No, VTH is the threshold voltage. Threshold voltage is defined
I said
by
the VDS. VDS means drains.
VTH. Sorry, I am not getting your question. Could you please repeat it again?
The V drain source, DS.
Okay, drain to source. Yeah, drain to source voltage for what?
So for the subthreshold region.
Oh, for the subthreshold region. Okay. So this plot you can do for various cases. See here. When we are plotting ID versus VGS characteristics, okay, then this plot can be drawn for different VDS. So you can choose VDS lower, you can choose VDS higher, right? But for almost any VDS, you will get a subthreshold region like this. So you have to see that for your device in which region you have to plot it. But whatever VDS you choose, you will get a characteristics which is quite similar to this. Yeah, its value would be different because with VDS these levels would be different, and the region of operation of this transistor in the whether it is saturation, linear, right? That is also dependent on this VDS and VGS, right? Relative value of VDS and VGS. So other than that, the type of the pattern would be the same. Is that answer your question, Shubhadeep? Shubhadeep, is that
Yes.
answer your question? Okay, thank you. Then what would be the total power dissipation? That is quite easy, right? So P total. So P total would be this P dynamic power dissipation, right? Then P direct path power dissipation. Then P static power dissipation. This is the static, right? This is direct path, and this is dynamic, right? And this would be the major component, okay, for typical like CMOS design. Okay, however, you have to also properly, consider the subthreshold leakage current to minimize this static one. Because if you are dissipating a huge amount of static power, then the whole advantage of CMOS is that one of the primary advantages for CMOS is that static power dissipation is negligible, right? So at any cost, you need to make this P static like pretty low. Okay, so here I hope that you have also noticed. So these two part, right, direct path as well as this dynamic, right, they depends on frequency, right? Because these two this happens during the changeover, right? And this P dynamic happens because of this charging and discharging. So this basically depends on this frequency, right? And this does not depend on frequency, right? This dynamic power dissipation is proportional to this VDD square. This is proportional to VDD, and this VP this PSAT is also proportional to with this VDD only, because it is basically the leakage current. If you have to see the power dissipation, then you have to find like VDD into this leakage current, I leakage, the total leakage current, right? So that way you can have some idea in your mind, like for or to some design something, which one would be important. If you have to scale down VDD, right, then which power is going to play the major role and all this stuff. Okay, so this was a brief discussion on the power dissipation in an CMOS IC, right? So let us now change this topic a little bit and discuss something else, which is so far we have discussed on the CMOS inverter, right? So let us also try to focus what about the other gates, right? For example, say NAND gate, NOR gate, XOR gate, okay? So what will happen? So before going to those things, those topics, let us just try to recapitulate what we have learned so far. So what is the general topology if you want to do design anything in CMOS logic? So basically it looks something like this, that VDD, then you have some pull up network, then in the below you have some pull down network, between you have this output, and you have to connect this input with both pull up network as well as the pull down network. So here I have shown multiple inputs because it is a general topology, right? Here also multiple inputs because this is a general topology. But for inverter, you know that there is only one input. So that way we can clearly we know this. If you have to design and CMOS inverter, which we have already discussed many times, right? So this is the typical construction, right? Or just to resemble with this. So let us say, right, this is V in, this is also V in, right? So V in one, this is V out, this is ground. So this basically gives this pull up network and this basically gives this pull down network, right? So you can see like from this general topology also we can arrive to go this CMOS inverter again, right? CMOS inverter, right? Okay. Now the question is then what about some other gates? For example, say, what about this NAND gate? Okay, okay. So, before discussing that, how you can design NAND gate, let us discuss what will happen. So, obviously, there are, you can see from here, this is the NAND gate, two input NAND gates, right? If the Boolean function it is implementing is f equal to a dot b bar, right? So, obviously, there are two inputs, right? So, two inputs means you have to use more than one NMOS and more than one PMOS, right? So let us see how this MOSFETs, NMOS and PMOS will behave when you connect them in series and parallel. And basically you cannot connect it any other way, right? You have to either connect them in parallel or in series, right? So let us see that. So when for NMOS, when they are connected in series, so these two NMOS when they are connected in series, right? So this NMOS, we have also discussed this NMOS, you have to use it as an pull down network only. I think this discussion should be in your mind only. PMOS cannot be used as a pull down network, right? This part we have already discussed, because if you use PMOS as a pull down network, then what will happen? The output, the minimum output will be limited by the threshold voltage of this PMOS. Similarly, if you use NMOS as a pull up network, then the maximum voltage that at this output would be VDD minus the threshold voltage of this NMOS. So you will not get the full swing, right? Output would be one threshold voltage below than that of this power swing. One threshold voltage below or one threshold voltage above the power swing, right, or the power line voltages. So from this perspective, we can definitely say this: if you are using NMOS, then definitely that NMOS is being used in this pull down network, right? So NMOS pull down network. So pull down network. So you have connected with some load, right? So you have connected with some load here. So now also you can see think of here, and this is grounded, right? So I've connected with some load capacitor here, and these are the AB connected in series. Now if both the inputs are on, like 1 1, right, both the inputs are 1, then only it can discharge, right? If it is 1 0, then it cannot discharge. If it is 0 1, no, 0 0, it cannot. So from this you can clearly see, if you are to connect two NMOS in series, so definitely that is going to give you and what function? Definitely that is going to give you an AND function, right? Okay. Now, what will happen if you connect two NMOS in parallel, say like this, right? Again, just think from the same perspective. right? Here Cl 0. So if you give here 0 1, yes, now it can discharge. If you give 1 0, yes, now also it can discharge. If you give like 1 1, yes, it can discharge. If you apply 0 0, then it cannot discharge, right? Because now both the transistors are off. At least one of the transistor has to be on. So basically, definitely from here you can say this is basically an OR operation. If you connect these two NMOS parallelly, right? But we are discussing CMOS. So when you're discussing CMOS, then definitely we should have PMOS and NMOS. So we have discussed what will happen with NMOS. Now let us see what will happen for PMOS. And definitely for when you say like PMOS, so in your mind, definitely it should come. PMOS is the pull-up network. It cannot be used as a pull-down network. So it is pull-up network. So pull-up network means if you connect this PMOS transistor in series, so it will look something like this. So this is one PMOS, this is another PMOS, and this output is connected with this CL, right? So this output has to be charged, or the CL has to be charged, right? So when it can charge, when this MOS is on, this MOS, both the MOSes are on. So when you apply, see here, both only 0 0, right? Then both these PMOS are on at that moment only the output can switch from 0 to 1. If you see for any other combination, let's say for 0 1 and 1 0 0 0 0, like either one of the transistor is off, and that basically makes this path broken. So this capacitor cannot charge, so output cannot charge, output cannot go to like high state. So then from here definitely you can see say that the PMOS transistor, if they are connected in series, so they will basically give the NOR function, right? So it is basically A plus B bar, right? From the same token, it is very easy to say if you connect these two PMOS in parallel, two or three multiple. So we are discussing with two inputs. So let us fix with that. But it can be more than two. It can be three, four, any number, right? So if you connect like this two in parallel and in the same configuration, then definitely with the same analysis you will find like this would give you and a NAND operation. So it is basically A dot B bar, right? So if you try to now generalize this discussion, okay, then what you will observe from here, which color to pick? Yeah, let's pick this ash color. Okay. So you can see from here, if you are connecting two NMOS in series, that basically gives you AND operation. AND operation. Now, if you see, if you connect two PMOS in parallel, right, like this configuration, that would give you an NAND operation, right? So you can see series here, series for NMOS, for PMOS, right? They are giving the complementary output, right? For this, you are getting AND. For this, you are getting NAND. But here they are in series. Here they are in parallel. Right, basically that means they are the dual network. Okay, now let me pick another color, say this color. Okay, maybe say this color, and see this, when these NMOS are connected in parallel, right, you can see here. So when they are connected in parallel, like for this, it is giving A plus B, which is an OR, right? But if you are connecting them in this fashion, that means if you connect a PMOS in series, they are giving you this NOR operation. So that means again NMOS in parallel and PMOS in series are the dual network, right? Okay, so based on this understanding, let us now try to design this F equal to A dot B bar, or the two input NAND gate. Then what would be the two input NAND gate structure from this transistor level point of view? So now we are doing the transistor level implementation. So definitely we know this A dot B bar. To achieve that, what we should have for PMOS, we should have this PMOS like this. This is A, this is B, this is VDD, and NMOS, what we have to take? We have to take its dual network in PMOS, in NMOS. So its dual network is when two NMOS are connected in series. Right? So now please take it out from here. Right? That is two input NAND gate, right? It is A plus B. So we have seen that when this is 0, like this is 0, this is going to be 1, right? And similarly when okay, could you please check that whether this circuit is working or not? Because I am only telling, and I'm not getting any response from your side. Please check it and tell me if this circuit is working as an two input NAND gate or not. Yes, Aniket, can you tell me? Ayushi?
Yes, sir, I'm checking.
Yeah, Ayushi, is it working as an two input NAND gate? Ayushi,
Yes, sir.
is it working as a two input NAND gate?
Sir, I was just making the truth table. So,
Okay, so could you please tell me what would okay, so suppose if I give 0 0 and 0 0 here input, so what is the output? Ayushi, please tell me.
the output would be 1. I mean, the capacitor would charge.
The capacitor would get charged and the output would be 1. Okay, so let us write that. So the output would be 1. Okay, for the next case.
For the next case also, it would be 1.
Okay, for this case,
1.
for 1 1,
For 1 1, the capacitor would discharge. So, 0.
the capacitor would discharge because now this is on, so it has a direct path to discharge. Right, so capacitor would discharge and the output would fall to 0. Right, so definitely we can see that it is working as a two input NAND gate. Yeah, thank you, Ayush. Right. So from here you can also probably have noticed that this complementary gate implementations, okay, by default, okay, is inverting type, right? So that means we are getting NAND gate, NOR gate, XNOR gate in a single stage. Suppose if you want to design AND gate, OR gate or XOR gate using a single stage means like this one stage, then that is not possible. You have to use an additional gate. Additional gate means additional inverter. So you design, and suppose if you want to design an AND gate, then you first design an NAND gate, then use an inverter, make an AND gate. Okay. So this is because this CMOS implementation is naturally like inverting type. Right. So please do remember this point as well. Okay.
Sir, in
Huh.
the previous page,
Previous page. Okay.
for NMOS, why did you write and or? Here also it will become NAND and OR only, right?
For NMOS,
Yes, sir.
when they are in series.
Yes, sir. It becomes NAND, I guess. Because only when both are one, the capacitor discharges, and it becomes 0.
Because when both the capacitors, yes, okay. So because you are taking it on minute, so because you were saying this 1 1 and you are saying it like this capacitor is now discharging, right? So
Yes, sir.
capacitor is discharging means now the capacitor will become equal to 0.
Yes, sir.
Okay, I agree with your point and you have a very good point. Yes, but actually while considering this and while I have written this and something else was in my mind and in my mind it was like this. Okay, this A, B, you have this applied voltage and you are seeing the output from here. Okay, because here we have explicitly mentioned like NMOS as a pull down network, so you have explicitly drawn like this. But suppose if you want to make a general understanding from here, then it would be like when both are 1, then only this output here going to be equal to 1, isn't it? So from that perspective, yes. But you are right, I agree with your point. If this is the circuit that we are considering for this purpose, then it should be NAND only. Yes.
Okay, sir. Thank you.
NAND and NOR, right? So that's why we are choosing both NAND and both NOR, because we have now fixed the pull down and pull up network here. Then that dual concept is not coming. Okay, dual concept will only come when you are considering both the network like this. Suppose P network, okay, 2P network like this, output is you are taking from here, and N network is also you are taking it like this. Okay, means same position. So we have not fixed the pull up and pull down position yet, but if you have fixed it, then it is like this. Yeah, thank you. Yeah, now let us pause for a moment and just think a little bit about what would be the voltage transfer characteristics of this two input NAND gate, right? So far we have discussed voltage transfer characteristics many times for different inverters, including CMOS inverter, right? But here we have two inputs, A and B, right? Then what do you think? Okay, what will be the voltage transfer characteristics? Means you have to plot this V out versus V in, right? So how does that look like? Okay, so definitely we are plotting V in. So V in means input voltages. So here it's not only one input, so you have two inputs. So there might be different possibilities, like A and B simultaneously going from 0 to 1 means 0 to VDD. Both A and B simultaneously changing from 0 to VDD. Or it might be A from the beginning itself is fixed at VDD. You are changing only B from 0 to VDD. Or the third case might be B is fixed at VDD and you are changing A from 0 to VDD. Right? This might be the cases. Okay. So let us take the very very simple case, which is like this. When A and B both are changing simultaneously from 0 to VDD. So that means what? You are basically shorted this A and B, and you have basically shorted A and B, and they are changing together, because if you have to plot in VTC, then you have to change this input voltage from 0 to 1. 1 means VDD, right? Maximum supply voltage. Then okay, this is an NAND gate. So NAND gate, two inputs are shorted. So this is become what gate? This is what?
Not yet.
Not gate. So it should not surprise you that this VTC would be similar to that of this NOT gate only, right? So, and also you can clearly see from here, right here. So basically, what if you are changing this means, suppose if you have see from here, you have two inverters. So basically, you have two PMOS. Okay, if you are if you are trying to compare it with the inverter, then what would be the difference? See here. V out, V in, right? So here there was only one PMOS, but you have now two PMOS connected in parallel, right? Two PMOS connected in parallel. Now remember this, two PMOS connected in parallel. So effective resistance reduces. Okay. NMOS, two NMOS, Here there is one NMOS. Here you have two NMOS, and two NMOS are connected in series, right? So what is happening? Suppose if you have used the same size, okay, compared to like this PMOS size, this PMOS size, this NMOS size, and this NMOS size same, then for this pull-up network, the resistance is lower, right? For the pull-down network, right, resistance is higher compared to this, right? And say you are getting these characteristics, BTC characteristics, right? Now let us say for the next case. Now you have fixed VDD, A equal to VDD. So now you have fixed A equal to VDD. So that means this transistor is always on, this transistor is always off. So that means for this pull-up network, right, compared to earlier, the strength has reduced. Strength has reduced means the resistance has now increased, right? So do you recall that for this type of inverter, when we have changed the ratios of like PMOS and NMOS, then what we have seen? We have seen that the VTC will shift depending on this PMOS and NMOS ratios, right? The resistances of this NMOS and PMOS. So here also what will happen here for the second case, okay, you will get a VTC which will probably look something like this. Right, but it will shift towards in the left side for this case. Okay, for the third case, yeah, you can expect that it should be similar to this number 2 only, but it is not actually. There will be slight variation between 2 and 3 because of this body effect. Okay, we are not discussing it right now because remember here this, if you are thinking that this body is connected with what? This body is connected with the source, right? And here this body is connected with what? This body is connected with the ground, right? So this body is connected with the ground, so it has no potential, means body potential is zero, but here you do have some body potential, right? And that will make the threshold voltage slightly different compared to this. As a result, the VTC will also be different between this 2 and 3, but let us not go into those details right now, but let us only understand this part, that compared to 1, the VTC for case 2 or case 3 would be different, right? For case 2 and case 3 would be different. So if these VTCs are different, because depending on the values, now you are going to change what is the relative strength of this PMOS and NMOS, means the strength of pull up network and pull down network, right? So see the beauty here. So the VTC here is dependent on the input pattern, right? So VTC is dependent on the input pattern, whether it is changing simultaneously or one is fixed, other is changing, right? Now, if the VTC is changing, I please recall our initial analysis, what is happening to the noise margin, right? Noise margin low, noise margin high, right? So basically we are changing noise margin as well if this VTC is shifting. So that way noise margin is also for this NAND gate or when the input gets when the inputs are when the number of inputs are more than 1, the noise margin is also dependent on the input pattern, right? See, this is the beauty here. Like for inverter, it is always fixed once you have designed it. But for two input NAND gate, NOR gate, or for any other multiple input gates, you will find its VTC is dependent on the input patterns, how the inputs are changing. And if the inputs are changing, means if the VTC is dependent on the input pattern, so definitely the noise margin is also dependent on the input pattern. So if you are considering only one case and designing the noise margin and all these things, so then probably you might not be doing the correct thing. You should consider like what is going to happen if the for different input patterns or different combination of input patterns. I think this part is clear to you. So, okay, now let us continue with our discussion from here. So we have now we have the framework for how to design any complex Boolean function in CMOS, right? So using that understanding, let us try to design now this one. Okay, so we have to design here this f is equal to d plus a dot bc. So you have to choose which is the, like, how you are going to analyze, right, this one. So first we will pick this one because it is inside this parenthesis, right, curly brackets. So b plus c we need to implement int. Okay, everything is inside bar, right? So that I should not means that is quite clear to you, right? So it is basically b plus c in PMOS implementation. So in PMOS implementation, b plus c means these two PMOS would be in series. BC series. Now that is been there is an AND operation between A and these two. So AND operation means in PMOS it is they should come parallelly, right? So it is A. So here it is VDD, and here you have D is again OR operation with the whole thing. So with this whole thing you have an OR operation. OR operation means for PMOS it is series. So this basically gives you this part. Okay, now we need to, this is the pull up network part. Now we have to design the pull down network part. So pull down network, what is going to happen? See, again B plus C means two transistors are in parallel configurations. BC parallel configurations. Now this is AND operation with this A. So here it is parallel, but in PMOS definitely it would be in series. Sorry, in NMOS definitely it would be in series, right? And with the total thing you have D in parallel. So in PMOS the D is in series. Here the D would be in parallel. Right, and you will get the output from here, isn't it? So if you have understood that part, then any Boolean function now you should be able to design using this CMOS logic, transistor level, right? Okay, yes. So is this part clear to you?
Sir,
Yeah, Shubhadeep, is
sir,
this
will it
clear?
give
Yes.
A for a bar? The result would
Uh, Sorry, would it give?
the result will be A for a bar.
The result would
If
be F. This F itself is the complement. F is this. So if you want this F bar, then we have to use another inverter. Means if you use only, or if you want to get D plus A dot BC without this bar, then you have to use an inverter after that. Otherwise, this would give you this only. D plus A B plus bar.
Sir, this series PMOS actually gives us B plus C bar. How can I use it for B plus C?
Series PMOS give us
NOR function.
yeah. Okay, where it is series PMOS, it is this one, right? If you have this A B here, we are getting A plus B bar. So are we not doing the same thing here? It is B plus C in series, so will it not get this operation?
Sir, so we are treating it after taking De Morgan's law.
After taking
That after doing the De Morgan's theorem, after that we are doing it.
Yes, 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 definitely, because here you have multiple factors, right? So you use De Morgan's, split it, and then do it.
So we can also draw this like at first we will draw B plus C whole bar, then put the output and in another CMOS inverter, then from the output we will get B plus C. Then we will, we will
Yeah, but
end that
then
output with A. The
right, but then
transistor
Suhayon,
still exists.
it will be then multi-stage, na? It will not be in
Yes,
one stage, right?
yes,
Multi-stage means you can make multi-stage, but if you make suppose a single gate in using multi-stages, then what will happen? You have this stage delay, this delay, right?
yes.
It has to calculate, na? Right that. Right?
Okay.
Okay. So
So,
if you have, yeah,
so for a single stage design, we can only have one overall large complement.
for one overall.
Like over here, F only
Oh,
has say one overall complement at the end. Suppose it
right,
was D plus A and B plus C bar. There was
right.
another bar on top of B plus C. How would we handle that?
There will be another bar on top of, no, it will not be another bar on top of this.
No, my question is if there was say another complement inside.
Oh, another complement. So, okay, good question. So in that case, probably you have to go for multi-stages, or you need to split it and represent it like this, so that there is only one bar like this on top of.
We can do that. We can do the B plus C whole bar as B bar dot C bar, and we will directly feed B bar and C bar instead of B and C.
Yeah, that means
We can
basically,
get that
Stuart, what you are doing, basically you are using, type of like Boolean algebra, means you are type of, simplifying it from that perspective, and yeah, you can do that. But, typically, like our goal would be we first represent it like this, in this fashion, okay, whenever possible, and then design it.
Okay, sir.
Thank you, sir.
Yes.
And so just one question
Yeah, yeah,
here.
sure.
The NMOS transistor where the A is getting as input, can that be in the lower portion also? There is no order like B plus A
A
into B plus
here.
the
Could
lower
not.
A,
Oh,
in
this
yes,
A in the lower.
yes,
Yeah, you are right. Yeah, that is a good question actually. So which one? So here actually you have this B and C. Okay, right. Whether can you like interchange, like keep this block up and make this A block
yes,
lower? So the answer is in some case yes or no. For like whether it is really possible or not, you have to see it from its layout point of view, which I am going to discuss not here thoroughly. I have already recorded one video, already uploaded in the drive. So if you open that suggested reading link, you will be able to see that. So I have already uploaded that part, okay? And so that depends on the layout part, okay? So whether you can do it or not. Hmm? So that is we have to analyze from that perspective. Yeah,
okay,
good. So here, before we go to some other topic, so two important terms which we should know in this context, because now we have discussed almost completed this static CMOS static CMOS inverter part. So these two terms are very relevant at this moment. And okay, not only the static CMOS inverter, we have also done the other inverters as well, right? Different configuration, pseudo NMOS, right? Inverter with resistive load, inverter with this load, that load, right? Different inverters. Okay. These two terms are like this: ratioed logic and ratio-less logic. So what do I mean by ratioed logic? See, this ratioed logic means here the logic levels are determined by the relative dimensions of the composing transistors. I will give you an example and then it will be very clear to you. Ratioless logic is nothing but the here in this type of logic design, the logic levels are not dependent upon the relative device sizes. Let us first go to the example and then we will come to the discussion. Say, for example, let us consider this one. This is what? This is? Okay, can anyone tell me this is what? What will be the output function here? We have discussed this type of inverters, like this type of designs in our class, so probably not using multi-input. So now the only thing is that I am using multi-input. So please tell me, this is what?
AB bar.
A B bar. Do others agree with Alisha?
Yes, sir.
Yes, it is AB bar, right? Because if you consider like here the CL, right? This is PMOS, right? PMOS is gate is grounded, so this transistor is always on PMOS, right? Always it try to supply current. So only until and unless these two are on, like A and B are on, this capacitor will be charged, right? We'll continue to hold the charge, means continue to hold the potential VDD, right? Obviously, I am expecting that here the discharging capability of this like NMOS part or the pull down network is much more compared to the pull up network, right? Because if the driving capability of these two is higher than this, then what will happen? The entire thing will be passed to the ground, so it will not be getting charged, right? So while designing this type of inverters, you should also keep this thing in your mind, right? So here it is quite easy, right? You can see here when this is on, only for that condition this capacitor will be going to discharge and the output is going to is equal to 0. So only for one combination output is equal to 0. So that is basically a NAND gate only, right? For all other combination, other output is going to be equal to 1, right? But see what is happening for this case. Okay, if you plot the voltage transfer characteristics, which we have already discussed for inverter, now we are extending it for this NAND gate. So this is basically this is called pseudo NMOS design. Pseudo NMOS design. Okay, this type of logic design is called pseudo NMOS logic design, where as a pull-up network you use an PMOS with its gate grounded. Okay, so what is going to happen here? You see, basically you have connected like this. Okay, and if you change the dimensions of these devices, okay, right, transistor parameters means basically the transistor, not parameters here, basically dimensions. I should not written here dimension. Dimension, then you see the voltage transfer characteristics is changing like this, right? So you can see from here VOL dash is fixed, sorry, VOH dash is fixed, but VOL dash is dependent on the transistor parameter. I think if you consider the resistive load also, for that case also we have seen similar things, right? That if you change the transistor parameter, this either this or maybe both will going to shift depending on the transistor parameter. But see, the same thing we are also getting here. Here also F is equal to AB bar, right? This is that just now we have done it. But here if you change it, here if you change the transistor parameters, then what you will see that the VTC will only shift the sidewise. There will be no change on these levels, VOL and VOL dash. So this type of design where this like peak output voltages does not depend on the transistor sizing is called ratio-less logic. Means the output voltages are not dependent on the ratio of these transistors. Okay, but this type of design where the output voltage does depend on the ratios of PMOS and like the PMOS width and NMOS width, then this type of design is called the ratio design. Okay. So why then basically we need to construct and ratioed logic. The whole purpose of this ratioed logic is that, see, for two input case, if you compare the number of transistor here, it is 3. Here if you compare the number of transistor, it is 4. So ratioed logic, because the entire for CMOS you need this, if you have two inputs, so you need two inputs for um, the pull down network, two transistor for pull down network, two transistor for pull up network. But here you need only one transistor for the pull up network. So that way clearly the number of transistors required to implement any Boolean function would be lower for this ratioed logic compared to the ratioless logic, right? So that is the sole purpose, okay, of if you want to go for this ratioed logic. But this does not come without any price. So the what is the price that we are paying here? So here we are basically reducing the robustness of our design, because now the design is not that robust like the CMOS. Robust in the sense means, you know, you change it, your output can drastically change, output voltage swing can drastically change. And the most important thing is that extra power dissipation. This is the most important thing, because here you can see that when this is on, this transistor is always on, there is a direct power path. So you have static power dissipation, issue, unlike this PMOS. So I think I have also written here, the general issue is the static power dissipation, unlike this, right? So I hope then this discussion that on these two terms, ratioed logic and ratioless logic, is clear to you. And if any logic is given to you, you should be able to tell whether it is ratioed logic or ratioless logic. Okay. Now regarding this part, yeah. So as I was telling that I have already discussed, like recorded and uploaded this one layout and stick diagram on this design, means layout and stick diagram part. Okay. So, and this is also included in the exam, which is in the next week, right? So please do read that. Just to give an idea what do we mean by layout. So far we have discussed about design, right? So once you finalize the design, then you have to send it for the fabrication, right? Okay, then how does it look? Suppose for design purpose, this is an inverter, okay, but when you make it on a silicon, okay, on a silicon flat surface, right, you have to fix different things, right? So there are foundries which you are going to send as a designer, right? You want you want suppose this one, then suppose you want to make this inverter, then when you talk to the foundry, then foundry will give you some directions. Okay, you do your design based on this criteria. Okay, there are some rules how you can design this. Okay, probably some software also they will send, and you have to use that software and make this representation, this circuit level, transistor level representation like this here. Okay, so here you can see this is basically PMOS and this is N well. Okay, so these dimensions are 6 lambda. What is this lambda and all these things? All these things been clearly discussed there, right? So this 6 lambda, this thing as a designer you have to fix. Means as a designer you don't have to fix. Means they will fix. The fabrication guys will fix design. Okay, and as a designer, when you are designing, you have to make sure that you are following the restrictions or the criteria that they have superimposed on your like layout part. Okay, for example, from here to here, this separation should be at least 6 lambda. So you have to keep that. Then from here to from here, this separation is 6 lambda. So all these things you have to keep in your mind and do the design. So just to give you an idea, so here you can see the width is like this PMOS width is 2, NMOS width is 1, because we know the mobility of electron is 2 times that of this electron. So to make both the resistance of both pull up and pull down network, we have to make the width 2 times. So you can clearly see so that we are using, this is actually PMOS. So this is actually the tap part, okay, where this for contact part. Okay, this is the polysilicon part, right? This is the polysilicon gate. Okay, and these are the like this terminal, right? These are these two terminals, drain terminal for the source. So this is that drain terminal, okay, for this PMOS. This is the drain terminal for NMOS. So you can see the compared to NMOS, the PMOS width is, so width is basically this one. This is NMOS width and this is PMOS width. Okay, and this is the gate, this part is the drain, this part is the source. So this part has been taken as a source contact, this part has been taken as a drain contact. Okay, so this is the general one layout diagram here, but here clearly you can see we have not considered this body contact. So here you can see for PMOS this is the body contact, This is for this body contact, body and source has been connected. So here we have not considered it in this layout. Okay, so layout is basically we have to see, means give the marks diagram. Okay, in fabrication for any to make any device you have to design some marks. Marks means, okay, how does that structure would look like on silicon surface? That is basically marks. So there are multiple levels of marks. We'll discuss probably if time permits in more details. Okay, so this is suppose this is one marks, this square is one marks, this polysilicon part is another marks. Okay, this triangle, like this part is another marks, this block is another marks, like that. Okay, so please do read, go through this, and if you have any doubt, please let me know on this Monday's class. Okay. Okay. Then I have also shared some information, some one lecture on this CMOS fabrication, right? So I hope that you have gone through that. So and you have not asked me any doubt so far. So I am assuming that there is no doubt in the CMOS fabrication part, right? But we should all be like, CMOS we have done, means we have done it quite extensively, so we know the CMOS fabrication. But there are some more nitty-gritty things regarding this MOSFET fabrication. So let us briefly discuss those part as well. For example, when the MOSFET was first invented, the MOSFET was fabricated using this. It was a gate last process. Gate last process means you make the gate at the last. Okay. So how do you do that? Okay, so or how people used to do at that time. Just to give a brief idea, and also on this I have written something on a handwritten document, so I will share that document today only with you, so that you can also, and all these step by step things are written there, means will be discussed, is discussed there. Okay, so no need to worry on that. Okay. So you can clearly see that starting, suppose if you want to design an NMOS, okay, if you want to design an NMOS, so starting material is an P-type silicon 100. 100 is the orientation of this, right? So the second step would be you do lithography, masking and all these things, and make these two regions, right? Means either diffusion or ion implantation, make these two source and drain region, N plus, N plus. Right. So the next third step would be then you grow an oxide on top of this. All right. So this is basically the gate oxide. Okay, for this case, grow an oxide for this case. All right. And the fourth step would be right on top of this oxide. Once it has been grown, right, once it has been grown, you deposit and pattern the gate metal. So say this gate metal we are patterning, and this gate metal is like this. Okay, and the fifth step would be you remove the excess oxide from the source and drain, because you need to take in contact from the source and drain, so you have to remove the oxide from the source and drain region, right? So you need to remove the oxide from that source region. So that's what I am doing here, right? And this is the gate. This is the gate, and you take contact from here, which is say source, and you take contact from here, which is basically drain. So it looks simple, right? This MOSFET fabrication, and this is the basic structure of MOSFET. Now the issue in terms of fabrication or practical realization of this device would be something like this, right? Say we are saying that we are placing this gate metal like this. How do you do that? Okay, there is no such process, means it is not an automated process, and with in automation also there is some inaccuracy, because you have to understand, like I have to place my gate exactly here. What will happen if you suppose shift it? If you have suppose shifted it, then what is going to happen? Probably let me discuss that by copying this one again. So copy and paste. Yeah. So oh my god, what happened? It has not copied the entire thing. It is not at all copying now. Let's see that if I can fix this issue. No, it is copying some part but not the other part. Okay, what about this? Can I copy it completely or no? Here also the same issue. Okay, does not matter. Whatever I do, it will come only up to this. Okay, no issue. I can fill this remaining part. Okay. Now, see, what is going to happen? Oh, it is really bad. All right, this one, this entire thing became instead of any straight line, it became something a curvy, quite curvy in nature, right? Yeah, this looks probably better. Yeah. Now, see, when we are saying that this gate metal, we have fixed it like this, but it is not a practical, right, thing. What will happen if while placing this gate metal, we have made some error. Okay, and what type of error? Suppose we have made this type of error, that this placement has been somewhat bit shifted in either source side or drain side. Now see what is happening. This gate is not been actually overlapped with the source. So when you apply some positive potential, you don't have any channel in this region between source and drain. So it will be always discontinued. There will be no current. Transistor operation is suspended, right? So for this type of devices, the uncertainty, okay, for aligning this gate is quite extensive, right? So as a result, to make the process reliable, what you have to do, you have to intentionally keep this gate metal bit wider compared to this length. Okay, so that you have sufficient overlap on this side and this side, such that with some tolerance in the error also, you end up with results some structure like this, not like this. Okay, so you have to make this overlap quite visible or quite extensive so that you can make a realistic device. But there is something like, as a result, you have to pay for something, right? When you do this, what will happen? You have capacitance between gate to source overlap, between gate to drain overlap. These are the parasitic capacitance, right? Right? Parasitic capacitances. So these are basically gate to source overlap capacitance and C gate to drain overlap capacitances. This type of capacitances will be quite extensive for this type of design or gate last design. Okay. So that was the issue, in initial fabrication of this MOSFET. So that's why people have to think, what can we do to solve this problem? Okay, and which has come up, people have come up with some, realistic issues. Later on I will show you this. Means today only in the next slide. So here one more thing is that here you can really make put gate metal. Okay, this may be gate metal. So that and initially when the transistor has actually been made, so initially people have used the metal as a gate. Not it was not a polysilicon, it was a metal, and that's where the name has come, metal oxide semiconductor, MOSFET. Okay, it is not polysilicon FET. Polysilicon FET, it is basically, then you can say it is POS FET. So probably then the name would have been different instead of this MOSFET, right? So the name is MOSFET because when the MOSFET was invented, at that time people used to do use metal as a metal to make this gate, right? But that was a gate last process where the gate you make at the last, but there was an issue in alignment. So alignment issue. Okay, so here I am not writing so many things again because I will write it here one thing. Please refer to notes. Okay, I am okay for details. Okay, that handwritten note I will share with you today. So please refer to note here, Ritus. I am just trying to cover this thing bit quickly. Okay, but if you have any doubt, please feel free absolutely to interrupt me. Then from there, the next technique has come, which is called the self-aligned gate technique. Because the alignment of gate or the placing of gate was so crucial in MOSFET technology. Because if you miss it, your transistor will not work. If you make the gate length bit higher compared to the separation between source and gate, then you end up with an higher overlap capacitance. Right? So we need some solutions, right? So that was the self-aligned gate MOSFET. Okay, and this has then revolutionized the MOSFET technology. Okay, but here also one more thing I have mentioned with low cost isolation. So we'll understand what is low cost bit later on, but what is isolation? So let us first think about that. So suppose we are making two MOSFET side by sides. Okay, so suppose CMOS. Okay, suppose we are making CMOS. So then we should have a PMOS, we should have an NMOS. Say this part is this. You can see here n plus n plus. So this is basically the NMOS and this is basically PMOS. Right. So we need to electrically isolate one device from the other device so that these two devices it's electrically isolated. Means electrically isolated means there is no channel okay between these two, so that these two will the performance of this or the working of this would not interfere with the working of this. So as a result, we have to isolate this device. So that is whole or the sole purpose of device isolation. Okay, and one of the technique for this isolation is called this locus. So here this is actually taken from this picture has been taken from the handwritten note only. So this is that locus. Locus stands for local, LO. This is LO. Okay, or you can say this or LOC, actually better to say this LOC. LOC is this one. LOC is local. This oxidation is that O. Okay, and local oxidation of silicon. This silicon is this is. So that gives the name locus. Okay, so local oxidation of silicon. So first let us discuss what is locus. Okay, how do you isolate? Once we understand that, then you will see what is self-aligned MOSFET fabrication process. So it is pretty easy only. So you have this silicon wafer, right? You make suppose if you have to design, like some transistor here and some transistor on this side. Okay, no, actually I am wrong. 1 minute. Suppose you have to make some transistor here. Some transistor means either it is n type or p type. Suppose you want to make n type transistor here and p type transistor in this region. I'm saying in this region you have to make. Okay, so you cover this two region with this pad oxide, which is basically silicon dioxide and silicon nitride. So previously this silicon dioxide and silicon nitride were on the total surface. Then you do lithography, pattern it. Okay, so after patterning you have this type of pattern. Okay, this is not the first step. Before that you have taken silicon, make a pad oxide, then deposited silicon dioxide, then pattern it so that this output looks something like this. Once you have done this part, see this region you have silicon dioxide, but this silicon dioxide is covered with the silicon nitride. Then you do further oxidation. Okay, so you can see here, everything has been written here with some these numbers as well. So this is B, so that means this is B. So then you do the thermal oxidation. So when you do the thermal oxidation, as this region are covered with silicon nitride, so this no further oxidation will happen in this region. However, as these regions are exposed, right, during the oxidation, so here silicon dioxide will grow, thick silicon dioxide will grow. And when silicon dioxide will grow, right, it will grow something like this. Some part will go inside and some silicon dioxide, as it is growth volume expansion, it will come out. So the entire thing will be like that. So it will penetrate inside as well as it will go somewhat bit out. Right? And the entire structure would look something like this. right? So you can clearly see now this structure will look something like this. So this region you have an oxide, this region you have an oxide, this region you have a thick oxide. These oxides are called the field oxide. Okay, maybe for on top of this oxide you can actually take one of the contact line. Okay, because see, you have to take the contact line from, route the contact line on the wafer surface. If you route it on a thin oxide, then easily below that channel will be, because you have some potential here, right, on this line. So below that some channel can produce, and that may again like create some issue, right? But as is the thicker oxide, right, then its threshold voltage is very high, right? Then probably at this voltage no channel will be created, right? So that is one advantage of using this thicker oxide. Okay, now let us remove now this silicon dioxide from here. So if silicon dioxide is been removed, which is end up with even, and you have end up with this type of structure, right? So once silicon dioxide is removed, right, then you also remove this oxide from this region. So now this is called the active area. Okay, this is called the active area. Active area, because now in this area you are going to make PMOS and NMOS, and now you can see this PMOS and NMOS are separated by this thick oxide. So this is basically the isolation. Okay, so while you do this thing, but you can see from here that what we have actually wanted, we could have actually wanted or preferred this type of structure, right? Here and here, this type of structure. But here you can clearly see, okay, during oxidation, there will be some oxidation here. As a result, this will try to expand, right? And this will try to pull this thing up, and this region will try to create a some scenario which is look like a bird beak, because if you just focus on it, see this structure looks something like this, right? So right, something like this, right? So now if you consider a bird eye here, right, and this structure is something like this, right? If you consider this, so it looks like a type of bird beak, right? So that is the issue. Oh, okay, why people call it as a bird beak problem, right? And like how this bird beak problem will influence. Okay, so earlier means you have assumed that my entire active area is this much, but now that entire active area has reduced because of this bird beak issue, right? Because that oxide has penetrated bit inside this active area, so that will reduce the active area. Particularly from the width side, it will affect more, because now you can think now you have a source here, right? So source and source drain here, then you have a gate here. But if you think three-dimensionally, right, then three-dimensionally this is the gate, this is the right, this thing, right? So this oxide is also there here, right? This oxide is also there here, this oxide is also there in this side, right? Try to think in a 3D model. Then this side also there will be bird beak, this side also there will be bird beak. So as a result, suppose you made this width as 1 micron, but effectively that width will reduce compared to that 1 micron because of this bird beak issue, right? So now we are in a position of where we understand like what is isolation, and we have also understood what is this locus process, right? But we are yet to do the fabrication process, right? So here basically after this, what you will end up with here like this, right? So you have this type of structure which is called the field oxide, right? And to make to as a further precaution, right, as I mentioned, like some metal line can go over this field line. To prevent the formation of any channel, what you do, anyway this is thick, but to be in a safer side, what you do, you further implant here something. Okay, because when you increase the doping of the substrate, your threshold voltage further increases. So that means you were saying that whatever be the voltage here, okay, in this line, okay, in this line, metal line, that voltage is not be sufficient to create any channel here. Okay, so that way you are basically saying that there is no possibility that there is any interaction between the device which I am forming here and the device which I am forming here, right? Okay, so now we are only focusing on the self-aligned technology. So let us only focus either on NMOS or PMOS. Techniques are same, only the doping will vary. So from two PMOS and NMOS, say this is NMOS, this is a PMOS on this side. So we have just dedicated our focus on this NMOS only, because if you understand NMOS, PMOS is almost the similar. So here it is NMOS. So it's basically, so I have taken only, you can see from here, I have taken only this part, right? Drawn only this part here. All right. Okay. Then after that, what we have done on this, so we have already this gate oxide. So on top of it, I have placed one polysilicon gate. So here you can see that metal is not possible. I have not used metal. I have used rather polysilicon as a gate. There is a reason why polysilicon is required, why we cannot use metal. I will just come to it, but first see the total process step. Okay, then you keep the polysilicon, then you do n plus or donor implantation. Okay, means basically you are creating this n plus and n plus region. This is polysilicon, which is nothing but a polycrystalline silicon. Polysilicon means polycrystalline silicon. Okay, this polysilicon means this is crystalline silicon, this is crystalline silicon, this is polycrystalline silicon. That is the thing. Polycrystalline means its orientation is, say if I say like this orientation is 100, then the orientation of the crystal is fixed here. But for this polycrystalline, the orientation, actually there might be many orientations inside these regions. It may be 100 some region, some 00 region, maybe 111 like that. So that is what a polysilicon is. So when you do this N plus implantation or donor implantation, so you basically form this N plus region. But at the same time, this is polysilicon, right? So this donor is also been doped here, right? So this gate, polysilicon gate, is also become N type. So remember that polysilicon for N channel gate is also doped with N type. Similarly, if you are making an P channel MOSFET, then you have to dope with an acceptor type. Then here it become P plus, here it become P plus, and the polysilicon, the gate metal, is also been doped with P type or acceptor impurity. Okay. Now why we have to means, okay, what is the advantage that because of this doping? Because the gate resistance, polysilicon typically has a very high resistance, sheet resistance. To reduce the resistance, you have to use the polysilicon, very heavily dope the polysilicon. Once you heavily dope the polysilicon, its resistance would decrease dramatically. And remember the RC loss, right? So this gate line, so we can, you have to understand in a 3D view. So this is this gate pattern, right? So if you are connecting some potential here, if the resistance is less, so if the resistance is high, then this is the resistance and this is the capacitance, right? So this resistance also plays an important role in determining the RC delay, right? So to reduce that, you have to also heavily dope this region so that this polysilicon is you heavily doped. So when you heavily doped it, its resistivity become very less, and you can at the time say now this polysilicon is almost equivalent to metal, right? It is almost equivalent to metal. So whatever the purpose was, the metal was serving because of very low resistance, that the entire thing you are also achieving by heavily doping this polysilicon. So this part should be clear to you with this. Okay. So what is the next step? The next step is you have oxide here, you have oxide here. So you need to remove this oxide because you have to take the contact from the source and drain. So remove the oxide, right? Okay. Then you have to take the contact from the source and drain. So that you can see clearly been shown here. And to prevent any further contact between this drain terminal and source terminal, between this source or drain and gate terminal, what we have done, we have initially deposited an oxide. So you can initially deposited an oxide everywhere, right? Then remove this region oxide, remove this region oxide, and then deposited metal here, deposited metal here. So now you see this metal with this oxide isolated from this gate polysilicon. So does this metal from this gate, right? So this is basically for isolation purpose. But so have you seen the beauty of the self-aligned process? So the self-aligned process is that here automatically this gate is being aligned between source and drain. Earlier you have to take the gate metal and you have to manually align it between gate and drain. But in self-align, as you are creating the gate first, so it is the gate first process. And then creating this n plus region, right? That basically gives you the advantage that you are creating the self alignment of the gate with respect to source and drain, right? However, when you do that, means after that you have to also do a drive in, means after any implantation you have to heat it at a very high temperature, because when you do implant it in this region lots of defects will be created. So when you hit this entire thing, these defects will actually disappear and this region will again become crystalline. Okay, so this is called the drive-in process, and you have to rise the temperature for this drive-in process to a very high temperature. And typically these metals are not suitable for that high temperature process. So as a result, there was no other way but the fabrication people have to switch from metal to polysilicon gate. So that was the reason why there was a shift from metal to the polysilicon gate. Okay. Right. However, you should also know in modern transistor, polysilicon cannot be used any further. So again, we have come back to the metal gate in modern transistor. Okay. So started with metal gate. In between, we have used polysilicon as a gate metal. Then again for modern technology, we are using the metal gate. So it is metal poly metal in terms of time line. Okay, I hope this part is clear to you. Self-aligned process, what is the advantage compared to the gate last process? Now another important part is here, this MOSFET with LED structure. If you see now some in your book, probably you have noticed some structure like this, that here the structure looks something like this. So this is source, this is drain, and you have seen something like this here, and here they have mentioned N plus, here they have mentioned N plus, here they have written N. Right. So this structure is called the lightly doped drain structure. That means, so this source and drain has to be heavily doped, but when you heavily dope it, there are some issues. So what are some issues? Okay. Suppose you have applied a high VDD. Okay. So electrons when flowing, they gain enough energy. Okay. Because of this electric field increases, your electric field increases, their velocity increases. So those high energy electrons are also called as hot electrons. Means you can say like high temperature electrons. So it is called the hot electrons. Okay, those electrons. And hot electrons, they have so much energy that they can even penetrate this oxide and like type of get trapped here or damage this oxide on this drain side. Okay, so to prevent that, what people have done, they have introduced a region which is lightly doped, okay, beside this N plus drain region. So let us, for the time being, let us forget about this side. Let us only concentrate on this drain side. So they have made this N region, lightly doped region here. Because why the reason behind is, see, this is a PN junction, right? So this N plus P plus. So when you have this N plus P plus, and if you are okay, and if you recall your semiconductor physics, when you have a higher doping, you have a higher electric field, right? If you have a lower doping, electric field reduces. So when you have lowered the doping, your electric field in this region has substantially reduces. So the electrons which were coming here, they do now do not have that much energy, okay, to create those type of damages. So that is the sole purpose of making this LDD structure, lightly doped dense structure. However, for fabrication point of view, how can you make it on the source, on the drain side? Okay, so to make the device symmetric as well as from to make the realization fabrication easy, people have make this N plus region, lightly doped N plus region on both source side and drain side. So that basically forms this LDD or lightly doped drain structure. Now the question is, how do you make this LDD structure? Not difficult. So if you consider the previous our discussion, so this structure we have already realized, right, in our previous self-aligned process. If you want me to show, so I have already written step E from the self-aligned process. So let us go to that step E. So this is basically that structure. So the up to this part is common. Okay, so we are starting from this part onward. So start with this, okay, which is a step E for self-aligned gate process. Then deposit an CVD or chemical vapor deposition silicon dioxide. So this is one technique by which you can deposit true. But what thickness at around these edges? So the thickness would be almost the 2 times of this deposited oxide, right?
Sir, I guess you're not audible for the
Right
last
here, this it cannot like. Sorry, could you please repeat?
So
Yeah, could you please
basically, for
repeat?
the last
Hello.
1 minute, you were not audible.
Last 1 minute I was not audible. Okay. Okay, then let me repeat it again from the last 1 minute. So, so this is like we are discussing about LDD MOSFET with LDD structure. So we have discussed like why we should have LDD structure, okay, to prevent the hot electron effect. Now we are trying to see how can we fabricate the LDD structure MOSFET. Okay, so for that we have started with this step from step E. This step E is the step which we have already discussed for the self-aligned MOSFET with low-cost isolation process. So this is that step. Okay, next step is after that you deposit CVD silicon dioxide. So you deposit CVD silicon dioxide, then the nature of this CVD silicon dioxide would be conformal in nature. Conformal means thickness is same everywhere. Okay, it does not matter whether it is up or down. Okay, if thickness is always same. But if you notice on this around these edges, what is happening around this gate edges, the thickness is higher compared to the other regions, right? Because of this edge effect, right? Then you etch it. Then you etch the silicon dioxide exactly by this amount. Okay, so you have different dry etching techniques. So use those dry etching techniques to etch this oxide layer by this amount. Okay, so you are etching it this amount, here also you etch it even this amount, this amount. But from here, if it is this much thickness is etching, so here from this also this will etch this much. Here also this will etch this much, right? So that means after this etching, you will left out this much of oxide. So you see, after this etching, you will left out with this much of oxide. So this remaining oxide on these gate sides are called the spacer silicon dioxide. Okay, so now you have some structure which is like this. Okay, and you have the spacer layer on the sides. Now you do N plus implant. So earlier when we have doped these two regions, we have doped it lightly. Okay, now we are doping it heavily, but you see this region, okay, when it is doping, this dopant will be prevented by this much thick oxide, right, in this side. Relatively less thick oxide on this side, relatively thin oxide on this side. right? So as a result, the doping profile would look something like this, right? This region would become heavily doped, which is N plus. This region will become heavily doped N plus, and this region, which was earlier there, which is lightly doped, so that would be lightly doped region would be here. Right? So you have, see, this region lightly doped, this region lightly doped, this is heavily doped. So this is exactly the LED structure, MOSFET. So MOSFET with LED structure. So this is basically that MOSFET with LED structure. So you can see that just by using couple of more steps, you can actually solve the problem of hot electrons or high energy electrons in that, right? So this is the fabrication technique for this LED structure. So all these details and step by step process has been written in this document, which I will share with you. Now to further discuss on this device isolation technique, so far we have discussed locus, which is already been discussed, and there is one more recent technique which is called this STI or shallow trench isolation technique. Shallow trench isolation. So from the now this locus discussion is already over. Now we are focusing much more on this shallow trench isolation. So what is this shallow trench isolation process? Here on that problem has again started, that if I do not touch, it will write. Okay, so probably I will not write anything here, okay, because if I keep my pen above, it will start automatically writing. Okay, so here it is silicon, right? On top of silicon, you have this deposited silicon dioxide, then silicon nitride, then photoresist. Photoresist is basically an organic liquid, okay, which you have deposit and then dry it and make it hard. Okay, then you open a trench like that. Trench means just open an window here like this, okay, so that you have then excess of silicon, you can access the silicon wafer, right? Now you use dry etching to etch the silicon. So once you etch the silicon, it will create a profile something like that. Okay, then do a thin, then remove this, photoresist, remove the photoresist, do a oxide, thermal oxidation. So that will create an oxide layer, thin oxide layer here, right? After that, you deposit a thick oxide. So you deposit a thick oxide. So you can see the total, this trench is now filled up with oxide, right? And then you do one CMP, chemical mechanical polishing. That means just do a type of grinding from this top, okay, and remove this much region, okay, remove this much region. Then if you remove this much region from the top entirely by this CMP process, then you will end up with this type of structure. Now, are you able to correlate this? So this is one of this isolation, right? This is another isolation. So here, this is the active area where you make your device, right? So this is another way by which you can isolate one device from the other device. And if you have to compare with the locus process, then you can see here in this STI, the surface become planar. You can see the surface is planar. However, if you see the locus process here, the surface is quite not planar. See, the surface is type of bumpy, right? Right? So for locus process, the surface is not planar, whereas for this STI process, the surface become planar, and this is one of the quite industry standard now process to use this STI for device isolations. Okay, to end up. Right, so we have seen couple of techniques. MOSFET fabrication has been explicitly discussed. CMOS process flow has been explicitly discussed. Now this slide give you, or this image would give you a final view on this. For example, okay, again that issue, I cannot write it here. Okay, so this is the NMOS channel. So you can see this is P substrate, we have made P channel, we have made N channel, and here we have created this N plus, this is N. So this is basically the with LDD structure, right? LDD structure like that. So it is CMOS inverter. If it is CMOS, I think I have written here, yeah, CMOS inverter. So if it is CMOS inverter, then this drain and this drain has to be shorted. So this is basically shorted. Now this is the source of this NMOS, this is the drain of this NMOS, this has to be connected with VDD, this will go to this ground, and here you can see we have used STI or shallow trench isolation to isolate one device, this N-channel MOSFET with that of P-channel MOSFET to isolate this N-channel MOSFET and P-channel MOSFET, right? So that is the basic difference. Like if you can use STI, you can use shallow means low cost to isolate these devices, right? Then on top of we have some oxides and we have taken connected. It's called the via. Okay, it's an via. So with this via you have taken this line. So this is called the metal line 1. Then you have this metal line 2 because there are multiple devices, not only one inverter, right? So you have to connect. So you do type of take multiple metal lines, go above, and connect the whole circuit together, right? Finally, you have this passivation layer. So only 3 lines are shown, but in modern MOSFET CMOS technology, you might have 6 to 7 lines, like metal lines, okay, one after one above the other. Okay, and you can also clearly see the width of the metal lines, thickness, and all these tips all also increasing as you are going above. So that means because this upper portion metal lines will handle much higher current. Okay, so for that you have to to even lower the resistance. So you have to make the like make them wider. Okay, so that is the sole purpose. And to reduce the capacitance between these interconnects, what you have to do, you have to use a low k dielectric, because you know capacitance is epsilon a by, right, the separation, right? So you can reduce the capacitance by reducing a or by increasing the separation, or at the same time by also reducing the epsilon. So here you use an epsilon or some a material whose epsilon or dielectric constant is lower. So that type of material is called this low K dielectric. Okay. So for example, air has a dielectric constant of 1. If you can get some some material whose dielectric constant close to that, that would be pretty good, right? Okay, so this is the type of whole overview of like how the CMOS has been fabricated, and basically like brief discussion on how devices are isolated, and also like what are the different isolation techniques, right? And why we have to shift from metal gate to polysilicon gate. Why polysilicon gate? Why can't we use metal gate for this self-aligned technique, right? All these things, I think you, with okay, from this discussion, you should have some clear view on that. Yes. So if you have any doubt, so it would be, yeah. So here one more thing. This is I got from this Intel journal. So here you can see the transistors are only here, right? Oh no, so actually not even here. This is actually that isolation. So this is the transistor. This is gate. This is source and drain. So this has been probed from here, right? See, the transistor is only for say only this much region. Only. Now I am using my mouse because I cannot use the pen. Otherwise, it is writing everywhere. So see how many metal lines are there, right? One after another. And see, as you are going above, the metal lines are getting wider, right? The thicker and become thicker and thicker, right? So this is an actual view, means you have taken a cross section and taken an actual view using scanning electron microscopy. So this is not an like type of schematic diagram. This is an actual view, right? How does it look like? So you can see even like compared to the width of the total this thing, this metal lines and all these things. See, not the width, the thickness or the height of this all this structure. The height of this device is too small, right? Too small. Yeah. So if you have any question, otherwise we will end. So I will, if there is no question, fine. So I will share this handwritten document with you after this class only, as well as this class notes. So remember, whatever we have discussed, including the shared videos, these are included in our next week exams. Okay. Yeah. And if you have any any doubt, so you have one more day, that is on next Monday, so we can discuss on that. Okay, so if you do not have any doubt, then we'll stop here today. is also 12.
So,
Yeah.
is the exam subjective?
Next exam.
Yes, sir.
Yes, type of, but if you mean like subjective means only you have to write descriptive answer, probably then that is not the correct expectation you should have. But it would be some type of numerical problems would be there definitely, some type of design problems, and maybe some type of short answer type questions might also be there, but definitely it is not an MCQ type.
And so, like from this region, will we be asked to draw these diagrams or just answer questions based on the concepts?
It can be both. Sometimes I can ask you to even draw, right? And definitely those will not be the structures that I have provided in my handwritten note and or discussed during the class. But those would be somewhat bit different. If you have understood this structure, you should be also able to draw those structures. Suppose here I have used the STI, right? Shallow-trench isolation to isolate devices. I may ask you to, draw the steps using a locus. Okay, what would be the step? Or maybe the vice versa. Okay, here there is only one channel, like only using the P well and N well, both wells are there. I may ask you, use only P well, okay, or use only N well. So that way the process flow would be somewhat bit different. So you should have the understanding and you should be able to modify those process steps accordingly. That is the
Thank you,
expectation.
sir.
Yeah. Okay then, if there is no further question, then let us stop here today.